Hello, hello, hello. I'd like to talk to you about the alkali-earth metals now. Now, the alkali metals were on the left side below the left side below hydrogen. The alkali-earth metals are the next step over. They have 2 electrons in that outer ring, 2 valence electrons. Now, that's not the number they want, and that's going to make them unstable. Not quite as unstable as the alkali metals, but pretty unstable. Now, let me show you some alkali metals here. I've got magnesium here, and I got calcium here, and I just want to take a few out here to show you. As you can see, they are pretty metallic looking. I hope you can see that. I believe you can. I have to check. And these are also, as you can see, very metallic looking. They are shiny like a metal because they are a metal. Now, calcium is usually the one that people wonder about because it's metal. Isn't your bones calcium? They don't look like this. Well, the reason why is that your bones are calcium and phosphorus and a number of other things put together. They're not pure calcium. In fact, you almost never find pure calcium anywhere. Anywhere. So that's why it doesn't look that way. Now, I want to show you these are metals. I've shown you they're shiny. I can show you, here's a piece of calcium. Now, the magnesium pieces are just too small. I can't really do the malleability test with them. They're just too small. But, okay, that one just flew away. Let me hammer this one. Well, they're not bending much, but they're not shattering either. They're going to bend before they shatter. They're malleable, like most metals. Calcium's a pretty hard metal, which is why it's really good for bones. You want strong bones, yes? Now, you'll remember what happened when we put the regular alkali metals in water. But these are not that reactive. They're not going to create fizzing and explosions, stuff like that. It's just not that reactive. It's reactive, more reactive than steel, but not quite that reactive. But that isn't to say that you can't get an interesting reaction. So you may have noticed there's something different on, oh, forgot. There's another test we need to do. How about the conductivity test? Now there's a piece of calcium. So, conductivity test. Do these conduct electricity? Well, here's our bulb. And let me plug this in. And so, we'll do the conductivity test. Here we go. Remember, if it conducts electricity, these should light up. That's probably way more than is safe. I'm going to put down a bunch of magnesium here. And we're going to try to run electricity through it and see if we can get the bulb to light up. So, here we go. And very carefully. Yes, it does work, okay. Okay, I'm not sure why it's not lighting up. This is, oh, there it goes. I guess there's just too many loose pieces. We're just having trouble forming connection because it should light up. It's trying. You know, sometimes experiments don't go exactly the way you'd like. Oh, here's a nice big one. There we go. Okay, there, that was one of the larger chunks. Now it won't get off. There we go. So yes, you can see that the magnesium was conducting electricity. Now the piece of calcium. See how that works. And you can see the piece of calcium does conduct electricity because it is a metal. But now, so they're shiny like metals, they're malleable like metals, they conduct electricity like metals, but I want to show you a way that they're different. They have all the physical properties of metals, but let me show you that they have some chemical properties which are mighty unusual for metals. Well, let me start out by putting the lid on this for safety's sake. And you may notice new item up here. So I have my torch going. These metals, because they have only, an empty, well, they only have 2 electrons in their outer shell, are less stable than other metals. So I'm hoping, are we still in the shot? We are still in the shot, hooray! So I'm going to start out by sprinkling as best I can some magnesium on this fork and see what happens. Now it's not as reactive as the sodium and the potassium. It's not just going to start because you put water on it, but when added to fire, you should start to see some reaction starting. And can you see some reacting going on here? Yeah, you can see some of the bits they're separating. It does burn. It burns. Now, if this were, fresher and newer, you would see it burning with a super bright white light. They use it in fireworks all the time. On the 4th of July, those bright white sparkles that they get are magnesium. You can see a bit of it. It's, oh, there we go. Part of the problem is these pieces are a little old and they're a little corroded, so they're not burning as easily as they would. There's a layer on the outside of them that is oxidized, and that's affecting its ability to burn, but it does burn with a very bright white light. Oh, there we go. Some of it's still going. So that's not typical metal behavior, is it? Burning like that. And this is a plumber's torch. I mean, this is standard, standard for plumbing. But there you go. Now you can see it's really starting to go. That is unusual. They use it in fireworks, but that's the reason why it's not used in a lot of other things. Also the fact magnesium ain't cheap, but that's rather unusual for metal. I think we'd all agree to that. Now, what about the calcium? Now, let's see, are we done here? Oh, this looks like it's about to go pretty nicely. We need to move on with our video, so. There we go. That's done. Now, let's move on to the next one. Now, smell the chlorine there. Okay, so let's disperse that, and let me take the piece of calcium, especially the one we've been hammering. Now, we've shown it's somewhat malleable. We've shown it conducts electricity. Let's see what happens when we heat this up. Now it's a big enough piece I can actually... And got to get it going. Now the problem is, again, it's kind of old. It's a bit corroded on the outside, so it's oxidized on the outside, and that oxidized layer kind of gets in the way of it getting going. And now if I had, more tools, I could grind it up and give yourselves lots of fresh, unburned pieces to attack. But here we go, calcium. Got to get it hot. I know, it's taking a second here. It's starting to burn. Okay, let's see if we can get it going. Ah, yes, we're starting to get... Yeah, you can see it's starting to burn now. Calcium, you can see it burns just like the magnesium, but it burns a different color, doesn't it? You can see it's getting that beautiful red color. And when you see a beautiful red color in the fireworks on the 4th of July, that is usually also, well, it's going to be calcium. It's not going to be magnesium, which gives you the bright white color. This will give you a nice red color. Now, there are other ones. There's strontium and barium and other ones. They tend to be more expensive. They also tend to be some issues with toxicity, where they could be poisonous. Since magnesium and calcium are in the human body, your body does have a tolerance to them because, well, frankly, they're part of your body. But you did see some glowing there. You did get to see some of the red flame. I'm sorry it wasn't a little bit better. Go out now, torch. But you can see, now, by the way, I think you're probably wondering now, well, you saw the fire with the alkali metals. You saw the fire with the alkali-earth metals. Does that mean that something like iron could burn? Well, the answer is yes, it could. But it's rather unusual that you're going to be able to create the kind of conditions that would cause iron to burn, where there'd be enough oxygen for it to burn, plus hot enough for it to burn, and not having it rust before it has a chance to burn, which is oxidizing. It's basically burning in slow motion. So yeah, iron could burn in the right circumstance. Rarely does, but yes, metals can. And let's see if it... All right. Oh dear. My tongue seemed to have melted shut. Anyway, I hope you've enjoyed this video. And, well, have a nice day. Bye-bye.